This is a sample lecture for the unit, or for the chapter that we just looked at, or the section that we just looked at. I'm just going to go through the questions here that I ask you. When do you construct a sign diagram instead of a graph? Well, what's a sign diagram and what's a graph? This is a graph. You're all familiar with XY graphs. This is a sign diagram, which just looks like a number line with pluses and minuses labeled. And you can see that when the parabola is positive or above the y-axis, if there's a plus here, when it's negative or below the x-axis, x-axis, it's negative here. And when it's above the x-axis, again, it's positive. So that's how you figure out if it's plus or minus. Now, negative 2 and 1 are labeled. Why are they labeled? Because those are the 2 points that it's an x-intercept, or y equals 0. So why would you draw a sign diagram instead of a full graph? And the simple answer is that you can draw sign diagrams very quickly, and graphs, of course, take more time. So when you do not need all this information as to how big y is, you just want to know if y is positive or negative, or you want to know when the graph crosses the x-axis, then you could just do a sign diagram instead. So the answer is, you use a sign diagram when you are in a hurry, when you need to do it fast. Make a sign diagram showing that f of x is undefined at x equals 0, positive when x is greater than 0, and negative when x is less than 0. Actually, that's right here. Look at this one. So you got 0, and it's undefined. So since it's undefined, there is a asymptote-like vertical dotted line here. And to the left of 0, it's less than 0, so we put negative. And to the right of 0, greater than 0, we put positive because it's positive. Okay? So, what are the 3 names of the points where f of x crosses between positive to negative, or just touches the x-axis? There's 3 names for the points where f of x crosses the positive between positive and negative. And the most common, you know, is x-intercept. So what are 2 other names? Well, you might know these 2 other names. One is zeros. That's a very logical name for this point. It's where y equals 0. And then there's the root, which maybe makes no sense. But roots is another way of saying when the function becomes 0. Okay. All right, and then we can start on these exercises. In the first exercise, what you're going to do is you are going to translate this graph into a sign diagram. And here's an example of that. You can see that when you translate the graph into a sign diagram, when the graph is below the x-axis, you put a negative sign. When the graph is above the x-axis, you put a positive. You put a plus sign. And when it's 0, you just simply mark the number. Okay? Now there's one case which we didn't talk about, which is when there's an asymptote, what do? You draw a little asymptote above the number. Okay? So here, it's not a 0, it's an asymptote. It's an undefined value at x equals 0, because when you put 0 into a fraction of the denominator, that makes the whole thing infinity or undefined. So we'll put an asymptote there. Okay? So that's how you do those. And the next ones, we draw sign diagrams for these factored functions. When you draw a sign diagram for a factored function, the first thing you're going to do is you're going to mark the points where it's 0. And when you have factored a function, it's very easy, because then you just look at this and you say, okay, when is this function 0? Well, it's 0 when x equals negative 4 or when x equals positive 2. So you mark negative 4 and 2 on the number line, and then you figure out, okay, when is it positive, when is it negative? And let's try to find a... Okay, so here's an example of that. We have a factored function, x plus 3x minus 1. Like I said, you take the negative 3 and you mark it on the number line. You take the 1 and you mark it on the number line. And then you just need to figure out when is it positive, when it's negative. Well, take a really big number like 100, and we'll put it in here, and we'll have 103 times 99. Is that positive? Yes, it is. So that means every number to the right of 1 is positive. So we mark it positive. What about a number between negative 3 and 1? Let's try 0 because that's a really easy one to do. Then we have positive 3 times negative 1 is negative 3. So all the numbers between negative 3 and 1 are negative. And then last of all, we do all the numbers between negative 3 and negative infinity. Let's choose negative 100. So negative 100 would be negative 97 times negative 101. Those are two big negative numbers, makes a positive, so it's positive. Another way you could do this one here is it's a parabola. And it's a parabola that opens up because the a factor is positive. In that case, you know that it goes from being positive to negative and then positive. So it's positive, negative, positive. Back to the problem sets. So that's how you do all the ones that are factored already. Now for these, G, H, J, K, M, N, these are not factored. So how would you do that? Well, first you got to factor them. Once you factor them, then it's the exact same process. How do you factor these? Well, there's a couple ways, but if you get one that you do not know how to factor, just use the quadratic formula. Substitute A, B, and C, figure out what the root is, the 0 is, and then you just write it out. Okay? Now next one. Draw Sion diagrams for these, and why are these tricky? Because it looks like there's only one root, right? So like what makes x plus 2 squared 0? Just x equals negative 2, okay? And then you would draw your lumber line, you'd mark negative 2, and then you would say, okay, what is the sign on the left? What is the sign on the right? Let's find an example for that one. That would be like this one. So we have x minus 3, quantity squared. So we know that the 0 is at 3, so we mark 3. Okay? And then we check a really big positive number like 100. 100 minus 3, 97 squared is a big positive number times a negative number, which is negative 4. We get a negative, so we mark it negative. Now the left side, we put in like negative 100, and we get negative 103 squared. That would be like a really big positive number. Again, times negative 4. Again, negative. Okay, so then you get negative on both sides of the 3. So that's why it's weird, because last time we would always get positive, negative, positive, negative, positive, negative. Here we get two negatives. What does that look like in terms of a graph? Well, it means that at 3 it's 0, but to the left it's negative, and to the right it's negative. So what does that look like? It kind of looks like a big hill, and the top of the hill just touches the 3, and then it goes back down. Okay, let's see if we have an example of that here. So it looks kind of like this one. Do you see how it's a big hill, it just touches the x-axis and it goes back down. So this one would look like that, where the values to the left of the negative 2 are negative, the values to the right of the negative 2 are negative, and right at negative 2 it's 0. Now what about the rest of these? Well, these are factored, so those you do just as I said. The ones here that are not factored, again, you need to use your factoring skills or use the quadratic formula to find the roots and then express it as a factored equation. Okay? All right, now, number 4, draw Sion diagrams for these 6 functions. Now, for this, you start out the same way. You're going to find out what the zeros are, and you're going to mark those on the Sion diagram. For example, this one, the zeros are negative 2, and then this would also kind of be a 0. It's not exactly a 0, because this is when the expression turns to infinity. But that is also a critical point. So you would mark negative 2, because that's a critical point. You would mark positive 1, because that makes the bottom 0, and that is also a critical point, but kind of in a bad way. So let's look at this example. You have x plus 1 in the numerator, you have 2x plus 1 in the denominator. So the two critical points here are x equals 1, because that makes the top 0, and negative 1/2, because that makes the bottom 0. Okay, can you see why negative 1/2 makes the bottom 0? So we mark those two. We mark 1 normally. We mark negative 1/2 with a tall dotted line, which is like an asymptote, because negative 1/2 makes the bottom 0. Making the bottom 0 makes the whole thing go to infinity. So then we have to mark this with an asymptote. Okay? Now we just need to mark the intervals, if they're positive or negative, and we just need to test one value inside the interval, and that determines the sign for the Sion diagram for the whole thing. So let's put a really big number in, like 100. We'll have 100 minus 1, 99. 100 times 2, 200, plus 1, 201. So we'll have a positive number divided by a positive number. That yields a positive number. What about a number between negative 1/2 and 1? Well, conveniently, 0 is a number between those two. We'll use 0. 0 minus 1 is negative 1. 2 times 0 plus 1 is 1. So that would be negative 1 divided by 1, negative 1. So that would be a negative number. So the middle, we mark negative. What about to the left of negative 1/2? Let's try a big negative number like negative 1/2. So that would be negative 101 divided by negative 200 plus 1, which would be two negative numbers. One negative number divided by the other. That would be a big positive number. So, again, positive. So positive, negative, positive is the result. Now you can finish these, okay? Now we'll answer the questions for page 69. Give an example of a linear function. A linear function is a line. You know what a line looks like. It's like y equals 3x plus 1. A line looks like this. Y equals 3x plus 1. Okay, instead of a and b, you're going to put in numbers. All right. Give an example of a rational function. Well, a rational function is just a linear function divided by another linear function. For example, like that. Okay, except for the a's, b's, c's, and d's are going to be actual numbers. So you could put an example of a linear function would be, or a rational function would be y equals 3x plus 1 divided by 2x plus 5, for example. Okay, for example, let's try to find one here. Like this. That is a rational function. Next question. Describe in your own words what is an asymptote. Well, an asymptote is like an imaginary line, okay, that usually you draw dotted, and it's something that the function approaches but never touches. So you can see like here, the function is approaching the line, but it never touches. Here, the function is approaching this line, and it never touches. You can see the asymptotes can be vertical or horizontal, and the function is approaching the line but not touching. Okay. Next question. Give an example of a reciprocal function. Well, a reciprocal function is a function that looks like something over a variable, which would be a reciprocal function looks like this, where it's like k over x, where k is like a number. So it would be like 3 over x or 5 over x. Okay. The simplest reciprocal function is 1 over x. Next question, on page 70. For a rectangular hyperbola, what is the value of f of x at x equals 0? This is kind of a trick question. This is a rectangular hyperbola, y equals 1 over x. What is its value at x equals 0? It would be at this line. Well, you can see there is no plotted point for this line. In fact, there is an asymptote at this line. So the value of the function at this value of x equals 0 is undefined. What is the value of x when x equals 0.001, positive 0.001? Well, if you put 0.001 inside 1 over x, you would get, I think, 1,000, right? Y equals 1 divided by 0.001, y would be 1,000. So when x equals 0.001, y equals 1,000. You can see the closer you get to the line, the bigger y gets. What about when it's negative 0.001? Well, negative 0.001, which is very close to 0.001, it actually goes in the opposite direction. When you put 1 over negative 0.001, you get negative 1,000, so it would be like totally down compared to this one being totally up. So you can see why the hyperbola here goes up and here it goes down, and they never touch the middle line, which is the asymptote. Explain why we simply cannot ask for the value of f of x when x approaches 0 for a rectangular hyperbola. Well, if I said, how does the function approach the asymptote here? I would have to say, what are you talking about, from the left side or the right side? Because the right side, it goes to plus infinity, and from the left side, it goes to negative infinity. So those answers are completely the opposite. So it's kind of hard to say how the function approaches the asymptote, right? Because it approaches it from two different sides in two completely different directions. So you might say, well, it approaches from the right, going to plus infinity, and approaches from the left, going to negative infinity. What values of x would you put in the function to find a horizontal asymptote? Well, the way you find a horizontal asymptote is you put big values of x. So you put like plus 1,000, you put negative 1,000, and when you do that, you will see that the rational function approaches a number like 2,